So for some reason I couldn't find my presentation slide. I think it got deleted for some reason, and just got to use the video. So hopefully that's okay. But hi, my name is Jonathan Collins. My research project was AI facial detection recognition. I used the category of computer vision for this project. Um, so just getting into it, I'm gonna go a little bit quicker here because my video is a bit long. So the problem definition, obviously with every model, you want to improve on accuracy and reliability. We make sure the model is precise when it comes to recognition and detection. So with like every model, we want to improve on that. Um, Obviously with cybersecurity, that has increased as the days go on. So that comes to application where we want to increase the security when it comes to facial recognition and things like social media, obviously um, security cameras kind of detect the person's face and recognize them as well. And then kind of going to motivation kind of goes based off that. We want to increase that accuracy and reliability with the model. Um, make sure it's able to detect those images with a lot of varying parameters and effects on it. Obviously, practical applications, we can apply it more into security as technology becomes more advanced as time goes on. Okay, so for my implementation, um, kind of going into the context of it, deep convolution networks, this is the basis for all computer vision face detection models. What deep convolution networks are is just basically an algorithm um, that uses pattern detection and layering. So as you guys see here on the image below, kind of shows how the layering works with convolution networks. So the first layer might detect like the general outline of the face, and then the second layer will detect like the more precise facial features and so on. And then the filters will pool together and then recognize a certain pattern with each person's face. And that's kind of how deep convolutional neural networks works, and that's what most facial models use as a basis. For me, I used three models that I applied or tried to re-implement. The first one is ArcFace. This one also uses DCNNs. Um, its main basis was facial recognition. So it would be able to recognize a certain person's facial features and detect that person's um, name based on those facial features. Um, and then I did OpenFace, which is more just facial detection to be able to detect what is a human face. This is the general basis and a bit simple. BGG face, this is an additive to ArcFace. This applies more parameters when it comes to facial recognition and um, detection. So it was able to apply more demographic features to a person's face. So it'll be able to recognize age, pose, sex, ethnicity, things like that. So those are the three models I tried to implement here in my project. And my goal was to combine them together, get the best of both worlds for all three models and put it into a project where I wanted to embed an image and then have it be able to detect that face, and then if it was recognize the name of that person and also its age and sex classification. I did my testing through the Friendscast. This was inspired by one of the GitHub repositories for use ArcFace, and they used the Friendscast kind of showcase how to embed images and recognize people's facial features. Um, so my mission outline and plan. So step one, I used the Google Colab environment. I tried first the Python or Visual Studio, and it's Python locally, but there's dependencies we're having trouble installing and stuff, and some libraries weren't working. So I tried to use Google Colab, and it was much easier to use those dependencies. So I started with that. There are some limitations with Google Colab as it can't really be large scale. Uh, but going forward, step two, I installed those necessary dependencies for my models. And then step three, I implemented OpenFace for facial detection. So my first step was to add OpenFace just to detect the basic facial features of a human face. And then step four, I would re-implement ArcFace for the image embedding and facial recognition. So ArcFace would first embed a bunch of images. So let's say like David Schwimmer for Friendscast, it would get a bunch of images of David Schwimmer, embed it, learn its pattern, its facial recognition, and then I would input another image of David Schwimmer and recognize his facial distinct features and say that's David Schwimmer. And then step 5, I would utilize the deep face library, which uses the VGG face model for those age and sex classifications of each tested image. And then, so my evaluation results, you can kind of see here, this is what happens when I input an image. I inputted all 6 images. This is what I outputted. The accuracy for face detection was very well. Almost all images were able to detect a face. I tried also on my own pictures of myself in different angles or poses and different lighting. It is very accurate to recognize my face. Um, Now, facial recognition in terms of the person itself, it was able to recognize each person distinctively. So it recognized Courtney Cox and every other Friends cast. And then this is where it actually kind of starts. The age and sex classifications weren't as accurate. When it came to age, it varied quite a bit. I believe that's because of the VGG face model isn't as accurate and doesn't have a good training model with it. So when it came to like I inputted images of children, it would say they're like 20. Inputted senior citizens, it said they were like 60, but they're more like 80 or 90. So age was varied quite a bit. If you're middle age, it was kind of accurate. And then sex also varied quite a bit, a few times, but it was somewhat accurate. As you can see here for Jennifer Aniston, it says man, and she identifies as a woman. They can kind of continue forward, kind of like gain more detail on the results. As you can see here, I inputted on the image on the left, this is what I inputted into it, and on the right, this is what outputted. First, it recognized the blue square, which is open face, will recognize the basis of the face, and then it would use arc face or inside face for the facial features of it, like the eyes, nose, lips, chin, and then it would go through VGG face for the age and sex classification, and then the arc face would recognize the person itself as Jennifer Aniston. Some key takeaways, obviously, mainly the accuracy of BGG face model for the demographic classifications weren't as I hoped for. It was also kind of incompatible when using the other models with ArcFace and DeepFace. I also had a hard code threshold value, which is the threshold value kind of determines the accuracy of the facial recognition. Um, so moving forward, with that threshold value, I'd like to create an algorithm that kind of bases off those inputted embedded images a more accurate value, so I don't have to hard code that value for the threshold. Um, and then also I want to improve the embedding for the model through ArcFace. Obviously, when it comes to VGG face, embedding those images for the age and sex classification, this model doesn't have enough embedding into it. There is another model called UTK face that I really wanted to use that used like 23,000 images for those classifications, but the Google Colab RAM couldn't handle that model at all. And then obviously, I want to improve overall on the facial recognition. And that is it. Anyone have any questions? Hello? Were you guys able to hear me through the entire presentation?
Yeah, we were able to hear you.
Okay. Um, I don't know.
Can you stop sharing?
I'm
I don't
still
I don't
sharing.
think your discussant is here.
My discussant isn't here.
Yeah.
I don't think.
Okay. Does anyone have any questions at all, or I guess we can just move on. They don't. They're not here.
Can you stop sharing? It's time for the next presentation.
Sorry.
It's time for the next presentation. The time.
9. Okay. I'll stop.
Yeah. Um, um, don't know. Let's see. Yeah. Can you see my slide? Hello, can you see my slide?
Yeah, I can see your slide.
Oh, sorry. Oh, shit. Running between screens, so sorry. Oh, shit. I'm some technical problem. I don't know why. I'm sharing my screen. Oh, shit. Oh, sorry, I'm having some troubles. Okay. Okay. Can anyone see my screen? Hello, can you see my screen?
Yeah,
Yes, we can see.
yeah,
Yes.
we can see your
Hello,
screen.
can you see my screen?
We can see your screen.
Hello, can you see my screen?
I think you can't hear us.
Can you hear us, Ismail?
Yeah, can you see my screen?
Yes.
Yeah, okay. Hello, everyone. I'm here to talk about my project, which is titled Geospatial Analysis with HRNet Architecture, a deep dive. This work explores the intersection of advanced computer vision and geospatial analysis, a rapidly evolving domain in geomatics. Here's the outline of my presentation: introduction, literature review, reimplementation, extensive study, conclusion, and feature study. In the field of geomatics, significant advancements in geoinformatics for geometry and topographic mapping have called for sophisticated analytical approaches. One of such approaches involves integrating HRNet, a state-of-the-art computer vision technique, into geospatial analysis. My study focuses on human pulse estimation and semantic segmentation to demonstrate HRNet's potential. To conceptualize my study, let's look at three influential papers that have significantly contributed to the field. These papers not only guide our approach, but also highlight the evolving landscape of computer vision in geospatial analysis. First, we have deep high-resolution representation learning for visual recognition. This paper's primary goal was to advance computer vision by introducing HRNet. What makes HRNet a game changer is its ability to maintain high-resolution representation throughout the visual recognition process, enhancing capabilities of image analysis significantly. The second paper, Deep High Resolution Representation Learning for Human Pulse Estimation, focuses on complex challenges of 2D human pulse estimation. Here, the efficacy of HRNet is demonstrated. The efficacy of HRNet is demonstrated in the precise estimation of human pulses, which is a crucial aspect of advanced geospatial analysis. And lastly, hand-to-hand human pulse and mesh reconstruction with transformers takes a different approach. This sketch aims to develop methods for human pulse and mesh recognition using transformers, offering insight into how these technologies can enhance the precision of spatial analysis. These studies collectively inform my understanding of the current state and the potential for resolution, representation, and pulse estimation in geospatial context. Just a brief overview of HRNet. What's HRNet? HRNet is high resolution net. It stands out. It stands out in computer vision for its unique capability to maintain high resolution across all layers, enhancing accuracy in feature extraction. This is particularly beneficial for integrated tasks in geospatial analysis like detailed land classification and precise human pulse estimation. Our first implementation involves semantic segmentation using Stanford background data sets. We employed the HRNet to categorize various elements in outdoor scenes, as you can see here, demonstrating the efficiency of HRNet by accurately estimating pulses across diverse human activities. Oh, sorry. The second implementation focuses on human pose estimation using MPI human pose dataset. Here, HRNet precision in detecting key human joints was tested, showcasing its capability in accurately estimating poses across diverse human activities. To extend our study, I applied HRNet semantic segmentation technique to the land cover.ai v1 dataset. This dataset was captured in Poland. It's an urban dataset. It involved detailed feature mapping in area imagery, emphasizing HRNet effectiveness in geospatial analysis. In conclusion, throughout the project, I faced some challenges due to limited computing resources and network complexity. Looking ahead, I plan to conduct more domain-specific experiments and utilize enhanced resources to comprehensively evaluate HRNet in geospatial analysis. Additionally, I plan to explore ways to optimize network complexity, which will be a key focus in my further experiments in the geospatial domain. Thank you. So if you have any questions, please.
Okay, thanks for the presentation. I have a few questions for you.
Yeah.
First one, so the HRNet, its architecture, how does it differ from other existing computer vision techniques? Can you elaborate a little more?
Yeah. I think the HRNet architecture, the way it's actually, like just as I mentioned previously, its architecture is designed in such a way that makes it stand out because it maintains high resolution feature maps throughout its network, unlike other traditional state-of-the-art. So that's actually like reduced resolution. HRNet maintains resolution throughout the entire process. This makes it give final detail preservation, and which is actually crucial for geospatial tasks because we want to get to the last accuracy, like minimum accuracy the maximum accuracy that we can get. So HRNet works better in that aspect.
Okay, the second question is, since you mentioned the geospatial analysis, how did you relate those to human pose estimation and the geospatial applications?
Yeah, just as I mentioned, HRNet for this study, HRNet is developed in such a way that makes it excel in areas such as urban planning. For the human pose estimation, that was the question. So in the case whereby you have surveillance camera or images that has like images that have people walking around, or images that contain people or in the features with the HRNet's architecture is developed such a way that it can estimate the joints of each of the individuals in the image, such as what I have here. You can see this lady jumping up. You can see with the HRNet, I was able to detect the joints of the shoulder joints, the elbow joints, the ankle joints of this person as well. So I feel HRNet actually offers precise analysis compared to traditional methods in this area as well.
Okay, thank you for your answer.
Yeah,
that'll be all.
Yeah,
because
thank you.
time manner. Okay, I think we should move on. Okay. You guys see my screen?
Yes.
Okay, perfect. Hello everyone. My name is Hans Kim, and this is my Tom presentation titled "Image Segmentation Using Transformer Network Implementation Using Geospatial Data." So, as an introduction, semantic segmentation can be referred as a pixel-wise image classification. Figure on the left shows the typical semantic segmentation task using cityscape dataset, which has about 30 different classes. You can see human, roads, trees, road signs, buildings, and everything. So it's basically you classify all the pixels into multiple different classes. And these are the example of some traditional image segmentation techniques. And as deep learning has emerged, various researchers have extensively researched for the adaptation of deep learning technique into these vision tasks. And one of the traditional and classical architecture should be convolutional encoder-decoder architecture, and the most successful and widely accepted model should be UNet model. The architecture you can see figure on the right here. And for my motivation, so self-attention-based architectures, particularly transformers, have emerged as the preferred models in natural language processing, while in computer vision, convolutional architectures maintain their dominance. So vision transformer first proposed splitting an image into smaller patches and converting them into a token so that they can fed them to a standard transformer encoder. And the figure on the right shows the attention from the output token to the input space. So my implementation was, I ended up using unit former for my model, since the unit former was the modification of the set former, and they can, particularly for geospatial applications, they can consider the global local context to capture both contexts for visual perception. And the dataset that I've used called is UAVID datasets. They have 8 different classes, and these dataset is for semantic segmentation tasks for focusing on urban scenes. So the results, the AdPoke ran about 40 times. At the end of the training, I got the most highest training IOU with a building class, while the human scored the lowest. And for visual analysis, I've brought some interesting figures here. So figure on the left shows in the yellow box, you can see there are actually shadows on the road, but the model have predicted as a tree class. And for the center image, you can see the flags the model have predicted them as buildings. And for the right image, the model actually have failed to predict the steady car class. For the conclusion, geospatial data has a different data distribution compared to conventional RGB image in terms of geometry, radiometric resolution, and spectral resolution. So for this study, I tested the feasibility of the transformer network in semantic segmentation, particularly for remote sensing applications. I have used UAVID datasets, and the model was selected. The uniformer was selected for my model, and my results, I've got promising performance, indicating that so this model actually can be used for the remote sensing applications as well. Thank you.
Yeah, thank you for your presentation. So it was very interesting. So I have these few questions to ask you. How does the unit format perform compared with the vanilla unit?
The thing is, I haven't compared the results yet, but definitely worth a try. But in the paper, authors claim that the uniformer actually outperforms vanilla unit in terms of accuracy and processing time as well.
Okay, yeah. So in your implementation, what is your modification in the because you implemented the paper, right? So what did you modify some parts? How does it compare with the original implementation?
Yeah, sure. So I basically re-implemented the code using the open source datasets with hyperparameter tuning. So, but one of the main takeaway that I've got from this project is that the transformer network actually really beats other conventional semantic segmentation models in terms of speed, which makes the model more suitable for real-time processing. Yeah, that was.
That's- Thank you. That's all I have.
Thank you.
Can you guys hear me and see the screen?
Yes.
Yep.
So today I'm gonna present my project, which is on challenges in multimodal learning. So basically, I'm gonna start with like what is multimodal learning. So as we all humans, we gain information to learn about the world through our 5 primary senses, right? Our ears, our eyes, our like the smell, and what we see, what we touch, etc. These senses can actually be seen as data with different modalities that are fused together to gain useful inferences. It's not that they are separately giving us information, it's that they are you take information separately from each of them and then you fuse them together to gain useful inference, which you would not have been able to do it if you had them independent. So it is thus necessary to study how to appropriately integrate these various modalities of input in the framework of artificial intelligence as the next step. And so in this project, what I did was I studied like 3 papers which dealt with like various aspects of multimodal learning, and then I implemented the paper 1, which was the on-the-fly gradient modulation. So with on-the-fly gradient modulation, what the paper was about was initial attempts at making multimodal framework dealt with naive fusions like concatenation, sum, or gated fusion. What they did was they took different modalities and they just concatenated it together, or they added the various features that they got, or they performed some kind of a gated fusion. But this paper recognized that with different modalities, for example, let's take audio and video features, they have different learning characteristics and behavior. They optimize at different speed, they converge at different, like at various steps. And so to naively just concatenate them is not right. So what happens is a naive framework would basically just follow the best performing unimodality and leaving the other modalities under optimized. So what this paper did was it got a discrepancy ratio depending on in each epoch. It got a discrepancy ratio which sort of calculated how well each of these performed, and then it with that ratio it changed the modulation so that the one which is underperforming is given more time to speed up and to like catch on with the one that is like best performing. The second paper was gradient blending. It was presented in CVPR 2020, and this paper was from Facebook AI, which dealt with modifying the optimization process again. What did this was it presented an unintuitive yet common phenomena that multimodal network underperforms in comparison to the best unimodal network, and it blamed overfitting on it, that multimodal networks usually overfit. So what they did was they introduced this OGR ratio, which is the overfitting over generalization ratio, and they use this instead of the loss function. Basically, they minimized this function. This function basically was how they defined overfitting was the difference between the validation loss and the training loss at different epochs, and the generalization was basically the change in the validation loss with epochs. The third paper was is multimodal, like better than single mode. Is a theoretical paper which says that theoretical understanding of multimodal network is very limited, and this tries to create a theoretical framework to analyze multimodal networks generalization, because till now it has only been empirically studied. So the paper argues that as multimodal networks will always have a better latent representation than unimodal, they theoretically should always perform better. But what they find out is that because it also has higher complexity, because it's also a better like a more complex network, And we always have like a problem with limited training data set. They usually fail in comparison to a unimodal network because that one is at least trained up to optimal level. So for the implementation, I implemented the first paper on a remote sensing data set. Basically, I took two different satellite data and which can be classified as different modalities. And at each training step, I took a ratio of both modalities losses. And so what it did was, I took a ratio of these losses and using this code, and it limits the gradient step for the higher performing modality. So based on the ratio, I multiplied that with each of the gradient step that it takes, so that the one which is higher performing gets limited, and the other modality has more chance to converge. So these were my results. This was the naive multimodal network, where you can see the different modalities having a graph, like the Landsat has like more error, and while the EcoStress has less error. And this was the training step. And when I did multimodal network with OGM, I found out that the one which has more loss during this stage where OGM was implemented, the actual loss of the higher modality gets lower, and then it goes to like a uniform ratio, like a uniform like number. And so, and even in the test data set, I found out that the multimodal network with OGM performs much better, better than a naive multimodal network. So yeah, so that has been my presentation. Thank you. Any questions?
Hi, can you hear me?
Yeah.
Yeah, so I think, yeah, in your results, like the difference is not like, I'm just guessing that the difference is not that huge as compared to the absolute value. It's like only 10 centimeters. So do you expect that if you like do additional experiments or other things that this accuracy might change?
So I discussed this in my paper as well. I think yes, the difference is not that much that I can conclusively say that this OGM works. But the better result for my analysis has been this graph, where at least it says that both of these modalities are now performing much better. In terms of the actual test data sets, there are many other things that can inform the results, and there are many other things in the experimental design that informs the results. And so yeah, I would say that even though there is like not an absolute uh, we cannot absolutely say that this works much better than the previous one, but we can say that there are certain changes, and the OGM one would be much better for few case, depending on case to case.
Oh,
Does that
okay,
make sense?
thanks. Yeah, it
Yeah.
does. Yeah, also one more thing. So in the, I think in the original implementation, I think you talked about it in the, not the implementation, the original paper in the second or third slide. Yeah, in this one. So it says that it's a softmax, to get the ratio, but I don't think that you're doing a classification sort of problem. It's more of like, it seems more of estimating something. So how do you go about that?
Right. Yo, yeah, sorry. I did not that's a good question. Actually, this is like part of you could say my new implementation. In terms of this problem was actually a classification problem where they used an audio visual data set, and the main problem in this in this paper was to classify the scene, what is happening there. So yes, this was a classification problem. Meanwhile, mine is a regression problem. So what I did was with softmax, what they are essentially trying to do is how is the model performing, how is the what is the performance of that model, and then taking a ratio on the on the difference in the performance of these two modalities. So using that logic, what I actually did was I implemented that my losses is sort of a metric for getting what is like my losses are actually a metric to analyze how the performance works. So what I did was I assumed that my ratios are the opposite of the losses. So the ratio for the Landsat would actually be the other's loss divided by its loss. Whereas in their paper, it was the softmax of Landsat divided by the softmax of EcoStress, like if their model works. And so, yeah, theoretically speaking, yeah, this would be my implementation. And
okay, thanks.
yeah.
Mhm.
Is that all? Do you have any question? Okay, I guess if there is no other question, I'll stop sharing.
Can you see my screen?
Yes. Hello, we can't hear you.
Oh, is it not audible?
Now we can hear you, yeah.
Oh, I just muted myself because the video has some audio in itself. It's fine. I'll just mute the video and present it like this. So, yeah, hi everyone. Today I'll be presenting my term project. It's titled Brain Network Transformer, which is using fMRI to predict autism disease status. And yeah, so let's go over some neuroscience background. So recently, the most ambitious pursuits of modern neuroscience is to model the functioning of the whole brain. And the whole brain can be seen as a natural computing entity that comprises of several regions of interest. And these regions of interest are specialized for specific functions. On the left, you can see that some regions are specialized for concentration, and some are specialized for taste, vision, etc. So this thing can actually, so MRI is a neuroimaging modality in which the data is collected as intensity versus time. And so this makes the data a time series data. And in order to model this kind of data, many papers have used something that's called correlation study. So this means that, sorry, this means that they will take different regions of interest and try to find the correlations between those regions in order to establish some kind of functional connectivity. However, this is fundamentally lacking a basic biological reference that brain regions are not connected one to one. For example, one brain region might have multiple other connections. In order to consider this fact, it is actually appropriate to model the brain network in the form of a graph. So yeah, this is the overall graph data structure. Here we can see that each node consists of some data, and the edges define how the data is related to each other. Oh, sorry about that. Yeah. So each node has data, and the edges define how the data correlates to each other. And we can use this sort of data representation to model the time series data of the brain. And we can use, in order to learn the high level representations of the functional organization, we can use a transformer to learn these representations. This is the basic architecture of a transformer that was originally proposed by Ashish Vaswani et al. In 2017. And in short, it has an attention head which tries to capture the long-term dependencies in data and short-term dependencies in data to get an overall representation. So the innovation in this paper was that they also developed a orthonormal clustering readout. So orthonormal clustering readout is a type of fuzzy clustering which assigns probabilities to each region of interest as belonging to a specific functional entity. And this is quite true because some regions of the brain might be performing a specific function 90% of the time, but not others in the remaining 10%. So using this kind of fuzzy clustering, I tried to re-implement the model. And this is the basic workflow of the whole implementation. So here we can see that we start off with the fMRI data, which is basically 3 dimensions cross time. And then we extract the time series data for each region of interest. And then we try to map the adjacency matrix for each ROI. And then this is fed as the input to the multi-headed self-attention module, which learns the dependencies and then performs a clustering readout and the clustering readout assigns each region of interest to a specific cluster. This cluster refers to a specific functional entity. So I implemented the given GitHub codes, and they have compared the brain network transformer that is shown in this sea green color with other graph transformers and neural networks. And you can see that the mean squared error is very low for the brain network transformer. Then I tried to implement the same for an open source data set. In this open source data set, it is called ABIDE, which is basically autism brain imaging exchange data set. And in this data set, they use the MRI data to train the model and make predictions based on the data to predict the sex and predict the sex and age and the disease status. So I actually re-implemented the model and increased the number of heads by 2 times. And this did not result in an increase of the accuracy or AU-ROC. As you can see, I have labeled the results that I got as mine, and I got a 78.1 plus minus 3.1 AU-ROC, and the accuracy was 69.5 plus minus 1.8. So this leads me to believe that the model was already quite good at what it does. And in future, we can probably try to implement some other kind of modifications, like increasing the number of layers or making a different kind of attention module. Yeah, that's it. Thanks.
Hey Shivam, that's a really great presentation. I found your topic really interesting. My first question was, what did you mean by fuzzy clustering? Could you just like clear it out? I didn't understand it, how it was different than like other clusterings.
Okay, so fuzzy clustering basically means that instead of saying that data point I belongs to cluster K, you assign it to the probability. You assign a probability to it that it has a 95% probability of belonging to cluster 1, but also 3% probability of belonging to cluster number 2 and 2% of belonging to cluster number 3. So it's basically like assigning a distribution of probabilities of belonging to clusters instead of hardly classifying them.
Okay. Okay, I think I understand. Fair.
Yeah.
And I just have like one other question, which was like with with like different types of computer vision problem, we have a CNN architecture, and with a time series problem, we have an RNN architecture, which are like related to, if it's a time series, then it would be an RNN, or if it's like because the recurrent like the nodes are attached like this. So here you are using transformers. So why do you think like transformers are appropriate for like brain mapping?
So
Is there any
I
reason,
actually,
or are they, yeah,
sorry,
continue.
no, continue.
No, so yeah, like, is there any like actual scientific reason for it, or is it like there should be, right? There should be any, yeah.
Yeah, so the thing is that in order to model the brain network, instead of one time series data, we have multiple parallel time series data. And if we need to model multiple parallel time series data and then classify them, transformer is a good choice because it can like simultaneously pay attention to multiple features at different levels. And by different levels, I mean that let's say we have 4 ROIs here. So ROI 1 and 2 might be very closely related to each other, but ROI 1 and 2 taken together might be very closely related to 4. So we have clustering at 2 levels. That's 1 and 2 are close to each other, and then 1, 2 is closer to 4. So that is a multi-level kind of attention.
Okay, and so like they are like more appropriate. So you think they are like the most appropriate ones for like brain mapping and things
Yeah,
like that?
because they follow a hierarchical ordering amongst themselves. The regions follow a hierarchical ordering in space and time.
Okay, yeah, makes sense.
Mm-hmm.
All right, that's all my questions. Thank you so much. It was a really great, like it was actually a really great, fun, interesting thing.
Thank you. Does anyone else have any questions on this? All right, and then I'll stop the share.
Okay, that's everyone.
Yeah, I think everyone's done.
Okay.
Yeah, I was the last.
Okay.
Lovely. Can we leave?
Yeah, I'll stop recording. Really good
Yeah, I think
presentation, guys.
Thank you.